go and so we saw how to last week. We saw how to do a linear model and how essentially we write we have some data which we have in the form of a table, and then we essentially express that table as the table of x's and y's as matrices, and then we formulated a cost function in terms of those matrices, and then we differentiated that cost function and equated to 0 to get a solution for the unknowns, and that's essentially the least squares estimate. So now if you have a bunch of points that are linear related and you want to find a model that predicts what the output should be for a particular input, you know how to do it. Today we're going to essentially do the same thing again, but instead of using an interpretation in terms of costs, we will start interpreting everything in terms of probabilities. And this interplay between cost and probabilities is sort of one of the fundamental things that you have to master as you go into deep learning and machine learning in general. To look at probabilities, we're going to revise Gaussian distributions. I hope you all went to the Wikipedia pages I asked you to last week and revised what your Gaussian is. Bell-shaped curves. We're going to do a very fast revision. But if you find you're a bit shaky with the concepts of covariance, expectation, and so on, then you do have to revise. You do have to go back to. And if you haven't learned them before, then just read the Wikipedia pages, really. We're also going to then formulate regression, that is the fitting the points to a line in terms of a probabilistic argument, and in terms of a principle of learning called maximum likelihood, which was one of the dominant one of the, I guess, great achievements of statistics last century. And then we're going to try to sort of dig deeper into this principle of maximum likelihood learning, and trying to see how does it relate to how cognitively we learn, humans could learn. I made this argument last time that if what you imagine and what you see are not the same, then you have to learn that you're not able to make predictions of the world about the world. And so, in fact, people who have some mental disorders, they start imagining things because it's not coming from their senses, it's coming from their heads. And you saw that you imagine most of the visual scene. You believe that you see the visual scene, but hopefully those illusions that I showed you convinced you that you actually are not seeing most of what you think you're seeing. It's coming from your head. And if that rewiring gets mixed up, then you start seeing things that aren't there. But they're just as realistic as the things that are there, because if you can't tell apart two things because a switch is wiring gating to from a different channel, then you really get that experience. It's real. So if you have some form of schizophrenia and so on, you feel you're being threatened all the time. You really are being threatened all the time by some alien or whatever, and it's a terrible thing. And so understanding how we imagine and how we sense and how that determines our experience of the world and how we learn is, to me, one of the most important things to do. Much of our experience of the world is clouded by how we're thinking that day. And so to me that's one of the key things that makes us human. We're also going to look at this from more mathematical principles and from sort of principles of information. So we're going to look at this concept of probability, and hopefully by the end of today's class we can, for very simple probabilistic models, very simple models, we're able to define clearly what we mean by entropy, what we mean by information, what we mean by likelihood, probability, by learning, by loss. And we're able to relate all these concepts and know how they all connect together. Okay, let's start with a revision of some basics. Let's pick purple. So the first thing is you need to know what a Gaussian density function is. It's essentially this curve here. It's a function of x. If you plot this function of x, it looks more or less like this. So the x-axis here would be x. The y-axis is the density function, p of x. And we know some properties of this density function. So for example, we know it is, for a Gaussian distribution, we know that its center is what we call the mean. We know that the way we describe its width is with this parameter sigma squared, which we call the variance. So the mean and the variance are the two parameters. So you have this bell curve. If you know the mean and you know the variance, you can draw it. So we call these guys sufficient statistics because they are sufficient to describe the whole curve. So if you know these two values, which we refer to as parameters, or sufficient statistics, we can describe the process. And so there's one more thing that we know about these guys, densities. Oops, sorry. Let me not complicate this. If we have the integral of p of x dx between minus infinity and infinity, and by the way, throughout the course, I will just draw this as the integral of p of x dx. So I'm not going to write minus infinity to infinity, and if I don't, then you should always assume that it's over the entire space. And the answer is? I am very happy to hear that. You guys are all on board. Which means that the area under this curve has a name. What's the area under the curve of a density? Probability. The area corresponds to what we know as probability. Okay. For probabilities, if we want to have discrete variables and continuous variables in the same grounding, the type of integral that we use is something called the Lebesgue integral. It's not the Riemann integral as you saw in calculus. It's defined slightly different. The definition in Wikipedia is very clear. And the main reason is because the Riemann integral is the limit of the sums of f evaluated at a point times a delta interval. And there are functions for which this sum does not converge to a single value. The sum diverges. And when we play with real numbers, functions that are, for example, 1 at the irrational, 0 at the rationals, you can get things that diverge. So that the Riemann sum ends up being insufficient. And so there's this minor refinement that we do to use Lebesgue integrals. For this course, the type of problems we're going to deal with don't require that we have that knowledge. So we don't need to go into those details. But if you do go into courses in non-parametric machine learning and statistics, then you do have to get a grasp of the differences, the subtleties that between those integrals. But for now, a good mental model to have is that if you have an interval, a small interval of width dx, you can think of the probability p dx as the height p of x times the width dx. So very much as we do for, say, Riemann. Because it's the area under the curve at an infinitesimal point. And so often, and this I just mentioned to you because of what you might find in books that might confuse you, you will often see this written this way, or you might see it written as P of dx. So if you ever see this, it's being people are referring to the same thing. But in this course, I will use the classical thing, which is like a Riemann integral. So the area is the probability, the curve is the density, things sum to 1. And had you had many points, what this is saying is if these are data points, if the red circles are data points, it's much more probable that you'll find red points, that the height of this curve is actually indicating the how probable it is that you'll find red points in that area. So if you look at this interval will have many more red points than this other interval over here. We call these the tails of the distribution. I guess think of a code, tails. And the reason why the parameters have sufficient statistics is because if you had 1,000,000 points distributed according to this, that is, that the number of points in a particular interval is sort of proportional to the height of this curve, or the area of this interval. If we had points that were distributed according to that, in that proportion, then if you knew mu and sigma, by knowing mu and sigma, you know exactly the proportion in which the points are going to be distributed. So if you had 1,000,000 points and you compute mu and sigma, then you don't need to store the 1,000,000 points, because mu and sigma are enough to reconstruct the properties of the points. In this case, how they are distributed. And that's why they call sufficient, that they're enough to reconstruct the properties of the points. As we go to more complex data, what our parameters, for example, in our convolutional models, our sort of filters that we get, like little faces and little edges and so on, those are the sufficient statistics that allow us to talk about all the images in the world. We're trying to find, despite the fact that we might have quadrillions of images, we're trying to find a representation that is small and succinct that describes all of those images. Because from that perspective, we've been able to compress the world into something that you can fit in a computer. Okay, so often I'm going to write P of x, so that's similar to if I write P of x. And that is a way of saying that this is a Gaussian distribution that has mean mu and that has variance sigma squared. So now this is just notation. By saying this, I'm just saying my data follows that curve, follows a Gaussian distribution. This is also the symbol that's used to simulate. And simulate is the same as imagine or hallucinate, or depends of. Jeff Hinton loves hallucinations. I mean, he loves to use that word. When you simulate from the model, you're basically drawing random numbers according to that distribution. So in a computer, you can say, give me x's that are distributed according to a particular mean and a particular variance. And the way that is done in a computer follows the following scheme. So first, so suppose you have this curve that is like this, the Gaussian distribution. If we want to draw samples from a Gaussian, then a common trick is to be able to draw random numbers from a uniform distribution. So a uniform extends from 0 to 1, and it has height 1, and then the area 1 by 1 is 1. So it's a probability distribution. And so a typical trick is you draw a number here, you then project, I actually made a mistake with my drawing. I need to draw one more thing. Okay, so we're going to extend this. I forgot to define an important thing. So we have the density is here, so that's x, and that's p of x. And then what I'm going to construct below is something called the CDF. And what the CDF is, as you move, imagine moving from left to right, and as you're moving, you're summing the area that you encounter. So when you get to the end, the area is 1. Initially the area is 0. So if you plot this curve, exactly at this point you would have seen half of the area, and beyond that you would have seen all the area. So the way we then we compute this function, which will look something like this. That's the integral that we call the cumulative density function of x. This is still x. And so now going back to how we draw numbers from how we draw is another word. This is just like throwing the dice, except we're throwing the dice with continuous numbers. And what we do is provided you know how to throw the dice for a uniform random generator, you can then generate samples from any of the other 1D distributions. Because you essentially build a cumulative, you project it, where it intersects, you map it to the domain. So you map the image to the domain, and then you get your sample. And if you keep doing this, you sort of kind of can see that intuitively, because the function is steep there, you'll end up with many points around this area. Occasionally, you get points drawn over there. So the proportion of points will be distributed according to the right density. So in a computer, this is called the inverse CDF method, and it's a method by which if you have an RND function, which is actually a pseudo-random generator in your computers, provided you can generate a sequence of pseudo-random numbers from 0 and 1, you can generate sequences from other distributions. So this process is what I will often say, that each sample or hallucination or simulation comes from a distribution P of x. Okay. So if you have lots of data like this, you can compute their mean and their variance, and then you can draw the curve. But if you also know the statistics, mu and sigma, you can generate data. So we have both the ability to do both things. How to go from data to mu and sigma, and given mu and sigma, how to generate data. And we always need to be able to do this. So for simple distributions, this is what you would do. For much more complex distributions, we'll see throughout this course how we would go about generating good simulations. Okay, some more revision. Actually, before you read this, let's start with a very simple concept: expectation. The expectation of a random variable x, which I used a symbol to denote it, is the integral of x times p of x dx, which for a Gaussian distribution is just the mean, right? Because the mean is the center of mass of this distribution. And and that is it's the definition of the mean. It's also called the first moment. And one of the ways we approximate this is, and I will use this symbol to mean approximation, is if you had n samples from this Gaussian distribution, you would approximate it this way. In other words, you would sample all the data, and you divide it by the number of data. So if you had several real numbers, 2.1, 2.3, 2.5, that is your data. You want to compute mu, you simply compute the average. And there is something called the law of large numbers that tells you that this estimate, this sum, actually does converge to the integral as the number of samples goes to infinity. And we also know how fast it goes. There's a lot of theory, which I'm sure a lot of you saw, like Hoeffding bounds and so on last term. You got to get a good sense of how quickly these estimators converge. Okay. Another way to think of this, when we go from here to here, is to think that what we're doing is we're replacing p of x times, we're replacing this with a histogram estimator. In calculus, there is this function called delta. And delta is defined basically this way. If you multiply delta at a times a function and you integrate over the whole domain, you essentially evaluate the function at that point. So a delta function, think of it as a sampling function. It just samples the function at that particular value. And so what we're doing essentially is we're replacing our expectation is being replaced by x, and then we're putting here 1 over n sum of deltas at xi. Okay, so what's that? Sorry, I missed. Let me know if I made any mistake on the slide. So essentially what you're doing is you're replacing p by several deltas. In other words, instead of having a continuous distribution over here, you're replacing by something that's a bunch of spikes. Not necessarily at regular intervals, but at irregular intervals. So we're sampling the distribution at points, we're replacing that inside, and then if you apply the property of the delta function, that's how we get to this delta. That is how we get this xi. And in most machine learning problems, the samples are data cases. So n is the number of data. We will have many examples. And you can think of nature as a distribution that's giving us data. And from that data, we will infer properties. And the rate at which those conclusions that we draw from the data are true, converging to what would be true if we had observed all the data, is something that theoreticians devote a great amount of time. We're not going to look into that, but this interplay between sample averages and expectations is essential. We will be always switching between the two. So you always remember the sample average is just another finite approximation to an integral. Solving integrals is sharp P complete. It's extremely hard. It's one of the hardest computational problems. However, as the dimension increases, however, approximating with sums is one of the ways in which we can attack that problem, by drawing samples at the right places. And this is essentially what folks call the Monte Carlo method, what we've just seen covered here. Okay, so one more. Okay, so now we can look at covariance. So we've seen what the mean is, and if you have two variables, x and y, then the mean of variables x and y of x and of the vector of variables x and y, if you have two possible variables, that will also be a vector, and that will be just mu x and mu y. Okay, so you now have two means, one in x, one in y. And one way to think about this, if you have two random variables, x and y, I'm avoiding having to define random variables and from scratch. You can think of random variables as quantities like temperature, pressure. They have some uncertainty associated with them. What is temperature? It's just the result of many particles in this room colliding and so on. It's not in many senses, just this macro variable that we use to describe a phenomenon that involves very detailed interactions of our particles. And you should think of random variables as just like that. They're just variables that we use to describe some phenomenon, and they have some noise associated with them. So in particular, if you have variables x and y, you might find that you might have one realization that says this is what x I observed, this is the y that I observed. When I observe this x, so they might be related somewhat like this. So you observe data now, and now the data has not just one dimension as in my previous slides, but now the data has two dimensions, x and y. So they're points in 2D. Each observation could be, say, the height and the weight of an individual. And so one natural question that we ask is, how does height relate to weight of individuals? And so we get to the concept of covariance, which is also related to correlation, even though I won't define correlation precisely. But in this case, for these points, we observe an interesting trend, which is if you increase x, then on average the variable y also seems to increase, right? Because we see that there is this trend here. So the higher the x values, the higher the y's. When that happens, we essentially say that the variables x and y do covary, or they have a strong correlation. In this case, a positive. The way we measure that is with this concept called covariance, which tells how variables x and y are related in this linear fashion. And to compute covariance, it's just like how you did variance in high school or earlier in your university. You subtract the means from each variables, and then you multiply them. And you also can talk about variance, which you could call, say, is the self-covariance, where you have x minus mu x times x minus mu x, minus the expectation. So recall that this is what I'm defining as the means, mu x and mu y. The expectation is the mean, and then in 1D, the variance just told you how broad the Gaussian was, but now you have more degrees of freedom. You could have something that varies like this, or you could have points that are sort of maybe placed in a circle like this. You could have something that varies where x and y vary in a negative relationship. When you have the points distributed in this way, like circles, then essentially by knowing x, a particular x, you can tell little about what. All you can say is basically an expectation for that x, your y is going to be 0. But you can't tell whether you don't have much information about the y variable. Whereas here, if I know my value of x, or all the information you have is that it's 0, or an expectation. Whereas here, by knowing the value of x, I can tell that my y is going to be high. So it has a positive correlation. So when I instead of using an x and a y, I now plug in here the same vector x, and I subtract the mean of x, which is a vector. I write this covariance. I end up with this matrix expression, which essentially is looking, if my vector got d dimensions, I'm essentially looking at the covariance or the linear relation between each dimension and every other dimension. So the self ones are called the variances, the other ones are the covariances. And they essentially tell me how linearly related each dimension is. So I have a vector in high dimensions, like this could be, for example, a DNA profile from one of you. Could be like, say, the expressions of 20,000 genes. And I want to know how these genes are correlated with each other. And this covariance captures, it's a very simple statistical way of capturing that. This allows me to now define a Gaussian distribution in high dimensions. A Gaussian distribution in high dimensions, for example, as I show here in 2D, looks like this. So you have x. X is now a vector that has two components, x1 and x2. So that we may define this as x2, this is x1. So it's a function in 2D. It's still bell-shaped. When you draw samples from it, this is how the samples look like. So that the samples are points in 2D. And depending on what the covariance is, you could observe any of these scatter plots. We call these scatter plots and so here I have I've chosen 2D covariances. They look like this. They're symmetric matrices. So covariance of x1 and x2 is the same as the covariance of x2 and x1. They're actually symmetric positive definite matrices, for those of you who have encountered that concept. And so if we have covariances that are 4 by 4, the means are 2 by 2, that means that if our points are in 2D, the important thing here to remember is that you need 5 parameters to describe your points. You now need to know mu1, you need to know mu2, the two means, and you need to know the two variances, the two diagonal variances, and then you need one of the off diagonals. And if you know that, that's enough to describe data in 2D. So if your data is described if the data that you measure for say height and weight of your patient is distributed in this fashion, x1 is height, x2 is weight, then you know that if you want to throw away all the points and only retain the quantities that fully describe how those points are distributed, you would just keep those 5 numbers. Okay. And so that's essentially a Gaussian distribution, a multivariate Gaussian distribution. Okay, so moving on. One of the properties, suppose now you have two Gaussians, a Gaussian in one dimension, another Gaussian in another dimension, and let's assume that these variables are independent. So in statistics, if we have a joint distribution, we can use the conditioning rule and the definition of probability of A and B is probability of A given B times probability of B. That's what I'm using here. If variables are independent, what that means is that x2 does not depend on x1. So x2 conditioned on x1 is, no matter what the value is x1, it doesn't affect what x2 is. And so independence just means I can drop the x1. x2 given x1 needs not be there. And I can now write the expressions for these two distributions x1 minus mu1 squared times 2 pi sigma squared e to the minus 1 over 2 sigma squared x2 minus mu2 squared. And I can group terms, and I can rewrite this as 2 pi sigma, and I'm going to define sigma to be the matrix that's going to have sigma square, 0 and 0, so that the determinant of sigma is equal to, sigma basically sigma squared to the power 2. And that allows me to write, I forgot the square root. That allows me to rewrite the product of the determinants of 2 pi sigma squared and the other 2 pi sigma squared in terms of matrices. And one property of, if you have a scalar times a matrix, and you take, that is 2 by 2, and you take that scalar out, because that scalar is multiplying each of the sigma, so it's A times A, so you have to square that scalar. So that's some basic properties of determinants. And if we proceed, then I have e to the minus a half, and if I group terms, I can write this as x1 minus mu1 and x2 minus mu2 times sigma squared 0, 0, sigma squared, and then I have x1 minus mu1 and x2 minus mu2. And let's use a curly bracket for this to make it clear. And I can rewrite this in this form. And so this is 2 pi sigma to the minus a half and I could write this now in matrix notation as the vector x minus the mean vector times sigma minus 1, and I can make this transpose times the vector x minus the vector mu, where the vector mu is the vector that has mu1 and mu2. So basically what I've...
to be a minus 1.
Oh yes, thank you very much. Because the sigma squareds are at the bottom and I'm moving up. So I've gone kind of quickly over this calculation because if you do machine learning, you do these all the time. I advise you to at home go slowly over these steps and convince yourself that these steps are correct. This is the multivariate Gaussian distribution, the Gaussian distribution for more than one variables. And the important thing here is if variables are independent, if one variable is not affected by another variable, that is manifest in the zeros in the diagonals of the covariance matrix. Okay, so now we can introduce the concept of likelihood. Let's assume that we have observed 3 data points in the world, and now we're back to 1D, and these data points are maybe 3 observations, 1, 0.5, and 1.5. So you're measuring some physical quantity, and you observe those 3 values. And you believe that those 3 values are governed by a Gaussian distribution. And your task, and you know that the variance is 1. You have some, from whatever knowledge that you have strong reason to believe that the variance is 1. So your question is, what is the mean of those variables? So what is the theta? And we know how you would compute it. You would just average them, right? The sample average was our approximation of the expectation of the mean. Here what I'm going to try to, with this very simple example, introduce the concept of likelihood. We're going to assume that these points are independent, again, that these points are not interacting. Like, for example, if I'm cooking, I can't say that every action that I do is independent, because whether I put something in the oven, that depends on whether I actually put something inside that tray. Otherwise, I'm just putting an empty tray in the oven. So my activities when I cook depend on previous activities. So in that case, my data is not independent. Each time depends on the previous thing. And soon we'll see, for most models, we have to relax that. But if all I have is realizations of images, I see an image and then I see another image and there's no connection between these images, those images are independent and I treat them as independent data. So a lot of the data that we will encounter, we will be able to treat as independent. And so independence in terms of probability just means that if I have 3 random variables describing my observations, or I have a random variable and I have 3 realizations of that, I can decompose that as, that should be a 2 there, as the product of those distributions. So independence means that P of A and B is P of A times P of B. And so now let's assume that I tell you there are 2 possible values that theta could have, 2.5 or 1. And then the question is, which one do you think it's more likely to be? Which theta do you think is more likely to be the one that generated a data? Any guesses?
1.
Yeah, if you just hide the data, 1 seems to be more obvious. The formal way to do this is, if you guess that theta is 1, okay, that's your guess, you would plot a Gaussian that has mean 1 and variance 1. And if you believe that the mean is 2.5, you would plot a Gaussian that has mean 2.5 and variance 1. And then what you would do to evaluate these probabilities is you would look at the height of each of the observations being 0.5, 1, and 1.5. And then what we do is we multiply those 3 heights, and the one that gives us the highest product is the one that's the most probable. That's the likelihood. That's essentially maximum likelihood. Each observation is treated as independent. We take their product, and if the product is the highest, that's the one that's most likely, that's the one that we accept. And for this problem, this seems to be an overkill, because we could have just averaged and that would be enough. But then we'll see that the same principle can be used for any of the models I described in the introduction, whether it's a recurrent neural network or a differential Turing machine and so on. We're going to use this same principle to be able to figure out which parameterizations give better explanations of the data, regardless of what the data is, whether it's code or images or text. Okay, so if you're Gaussian distributed with mean, so the first thing is, if you have a Gaussian, you can just essentially this gives you a noise model of, about the mean. So if you have a random variable that has got this value, you can describe it in terms of a height plus an oscillation signal. So a height which is this height and then some oscillation. So I can take this outside of the n. And so basically what we've now what we've been saying is that the y's are distributed according to a Gaussian distribution. Okay? So now we're going to look at regression, and we're going to allow for x's as well. So now we have a process that takes x as input and creates a y as output. The uncertainties in the y's, the probabilities over y. X is given. There's no uncertainty. In our model so far, what we will assume is that there's no uncertainty in the x's. Someone gives you x, and then your goal is to predict y. X is given to you. It's a known input. And the parameters, we're also going to condition. There's no probability in the parameters. The parameters are quantity whose value you're trying to estimate. We'll see later there's something called Bayesian stats, which takes a different view on this. But from the perspective that we're looking at now of maximum likelihood, we're going to describe the probability of a vector whenever you have now regression where you had this vector of y1 all the way up to yn observations, and you had a matrix. So we had this vector y, and we had this matrix x, which had x1 all the way up to x1d, and then all the way up to xnd, so that as we had in the previous class. Then to describe the distribution, we will consider the distribution of each individual point y, and I will soon draw a diagram illustrating exactly what we're doing. But if you do this, and if you write this distribution for each point, so we basically say the mean of the point is a line. It's the line x times theta. And the rest is kind of tedious math. If you have a product of functions, especially exponentials, that's e to the sum. And then a quadratic form, as we saw last week, can be written as the dot, can be vectorized and written as the dot product of y minus x theta. So this starts looking interesting. Let me write it a bit more cleanly here. Because what you realize is that the probability of data for some parameters this line, by the way, I said it in words, but let me emphasize, this line in my notation means given. Anything to the right of that line is given, so you see it. There's no uncertainty about it. The only uncertainty is about the variables that are to the left. So data here is the random variable, because the universe is giving us data by sampling from some distribution. That can always basically be written as 1 over some constant, which we typically call z. That's the standard notation for the normalizing constant. And it's the constant that ensures that things sum to 1, so that you have a probability distribution over the data. E to the minus loss of data and parameters. Parameters. Okay. So if you take a loss, you negate it, exponentiate it, and then you divide everything to make sure that that you get an integral that sums over the data that sums to 1. You get a probability, and we will interchangeably go from loss to probability by doing this. If you have a quadratic loss like this, the mean squared loss, the mean squared error, mean squared loss, quadratic loss, then if you exponentiate it, multiply by a constant, which in this case is 1 over 2 sigma squared, and divide it by the right constant, which in this case is this 2 pi sigma squared to the minus n over 2, then you get a probability distribution. And this will be true for other types of data. Now, let's go and revisit our example last week, which was how to fit a line to observations x and y. Okay, so last week we saw that, okay, so our model is a line. So we have, the setting is, we have the y variable here, we have the x variable, and we observed several points. Something like, say, this. Okay, and so what we did is our task was to fit a line to these points, and we did this by requiring that these springs come to a minimum energy point. So that was our way of minimizing loss. So, and in particular, each of these guys is a point. These are the y coordinates. These are the x coordinate. This is the y coordinate. And the prediction here is what I call yi hat. And yi hat is essentially theta 1 plus xi times theta 2 is the evaluation of the model. What we're doing with probabilities is we essentially are placing a Gaussian at each of these points. Okay? Because that's what we've been doing in the math. We said there's going to be one Gaussian for each y, and we're going to multiply them. So I'm going to put a Gaussian here. The center of the Gaussian, the mean, is x theta. It's the line x theta 2 plus theta 1. So I have a Gaussian like this. And then for this point, I also have a Gaussian. And for this point, I also have a Gaussian. Let's do one more. And the probabilities of each point are these heights in black. And I've only done it for 3 points, but you would, to not clutter my drawing, but you would do this for every point. So each point is a Gaussian, is distributed according to a Gaussian. So the uncertainty here is in the vertical. Just like least squares. In least squares we minimize vertical distances. Our uncertainty here is in the vertical. And instead of minimizing, we can do two things. We can minimize the length of the springs, or we can maximize the vertical bars. It makes sense because what we're doing with the loss is we're negating the loss. And if we negate a function, and then we just make sure that it integrates to 1. But if you have a function, if you have a function, a probability that looks like this, and you negate it, then you get a loss. Here you find a maximum, here you find a minimum. And that's basically all you need to know to compute thetas. And this essentially is a visualization where you're doing with maximum likelihood. You're saying that each point, the height is Gaussian distributed, and then you're making those probabilities. You're making the multiplication of all the black bars as high as possible. And you can see that you would have to shift, move the line until those, the closer the line goes through the point, the higher the black bar is. Okay, so this forces your line to again equilibrate nicely at the data points. Again, if we had outliers, like I mentioned last week, this would be problematic. This model would fail. How do we compute this? Just like we did last week. The rest is really tedious. Well, once you know how to specify a distribution and you know how a distribution relates to a loss, basically the distribution is e to the minus a constant times the loss. if you want to compute the solution, what's the most likely mean? What's the most likely theta? One trick that we do is we write the log likelihood. And it's called the likelihood because it tells you the likelihood of the data given a particular model. And the log likelihood just allows us to write this in a form that is more amenable to the computing. From analytical derivation perspective, I forgot a log.
I just had a question about the linear regression of the previous slide. The problem with taking the vertical distance as opposed to the orthogonal distance.
Oh yes, that was a question someone posed last week. So this is not ideal. As I mentioned, one of the things you would want to do is measure the distances like this.
So what if, for example, what if the line was vertical?
If the line was vertical, you're in trouble.
So not if you take the distance as orthogonal to the line, then you're not.
Oh yes, but under the maximum likelihood perspective of the Gaussian as we've defined it with the uncertainty device, the least squares, you are in trouble.
So you could also take the square distance orthogonally to the line.
But that would not be the same model, that would be another model. And this is what we do in statistics. We look at this, we have a model. In school you've been using this model all the time and you believe it and you do calculations. But indeed, you soon realize that this is just a model. And sometimes to describe data, you need to come up with better models because this model will not suffice. And you have to be very careful when these points are vertically. And that will be motivation for the next lecture. But to finish this here, just a few more mechanics very quickly. We write the log likelihood. Sometimes we write the neg log likelihood of theta, which is just n over 2, we just negate it. Okay? And the reason why you negate it is because now it's more obvious that this is a loss function for both x and both theta. So by taking the negative log likelihood, we go from probabilities to loss functions. Or loss functions, as I mentioned, they're also known as energies and so on. So you need to maximize, the goal here is to maximize this, the goal here is to minimize. Okay, taking the minus of a function just flips it. And so if I want to maximize, and the log is a monotonic function, so it doesn't change the location of the optimum. So if I want to find the maximum for probability, all I need to do is find the minimum of this loss. And so I need to compute the derivative with respect to theta of the first term. Doesn't matter because it doesn't involve thetas. And so I just need to compute the derivative with respect to theta of 1 over 2 squared, 2 sigma squared, y minus x theta transpose y minus x theta, and equate it to 0. But this is exactly the calculation we did last week when we computed the least squares. And so once again, when we equate to 0, we get that the theta maximum likelihood, the estimator maximum likelihood, is x transpose x minus 1 x transpose y. We get the same answer as before. So maximizing the likelihoods, this is the mathematical way of algebraic way of verifying our picture. Maximizing the likelihood is the same as minimizing the law of the quadratic loss. And you can also do it for the variance. So I did it in more detail on the slides, which I'll upload this evening, where you take the derivative with respect to the variance, you solve for the variance, and you get your standard estimate of the variance. So no surprises there. If you need to make predictions, So now you learn, basically the process of learning gave you theta 1, which is the slope, and gave you theta naught. So if you're now given a new test point that you hadn't seen before, if you want to compute its most likely, the corresponding most likely value, you essentially compute the mean, and that's your prediction. So the prediction is you evaluate the likelihood at that point. That's not what Bayesians do. Bayesians do something called marginalization. They would integrate over all the possible values of theta that you could come up with. They assign priors to theta. I'm not going to do Bayesian statistics in this course because I just don't have enough time to cover it all. But be aware that when you're being frequentist using optimization techniques, that we're going to be using throughout this course, we get very good estimates of the function, but often we have terrible estimates of the uncertainty, unless we introduce more sophisticated models. The Bayes way, using a posterior predictive mean, tends to be not confident where there is no data, which is what you want. Maximal likelihood is overconfident. So this is problematic. Keep this in mind. You're good where there is data. Where there is no data, don't trust it. Quickly, another random variable we'll use in this course is the Bernoulli variable. This is the other simple distribution. It's just a distribution for a coin with probability theta. The coin is tails, with probability 1 minus theta, it's heads. And so if the coin is 0, 1, you can write the probability of it being 0 or 1, of x being 0 or 1, as in this form. It's either theta or 1 minus theta. If you sum the two, you get 1. You can draw it this way. You can draw it with a picture. Or if you really don't like to write too much, then you very succinctly write it in this form. Theta times 1 minus theta, and then theta to the power x, and then 1 minus theta to the power 1 minus x. This is the form that you will find described in all the neural network implementations. So Bernoulli noise is very useful when we're doing classifications. You're trying to predict, for example, whether a patient is healthy or not healthy. So the output of the neural network will be governed by a Bernoulli distribution. And essentially this is where probability is going to come in, how we interpret the outputs of the neural networks. And so that just gives us a succinct way of describing it. You can also compute the maximum likelihood estimate, and no surprise, theta will be the number of times you saw 1 divided by the total number of coin flips, and you can verify that by computing the log likelihood differentiating with respect to theta and so on. The Bernoulli variables also allows us easily to define a quantity called entropy. And what the entropy is just the probability times the log probability summed over the domain of the random variable x, in this case, and importantly negated. Now, entropy is a measure of uncertainty. I will illustrate that with an example. If you take a Bernoulli random variable and basically substitute in this expression the expression for the Bernoulli random variable, and I substitute x equals 0 and x equals 1, I solve the sum, I end up with this function, and what I do is I go and I plot it. And if I plot it, I see that my entropy is higher when the coin has probability 0.5 of being tails or head. And that's essentially basic. An unbiased coin, you have very high, if I start flipping an unbiased coin, you have very high uncertainty as to whether it's going to be tails or head. However, if I put a lot of lead on one side, and most of the time it comes out heads, you have less uncertainty. You'd be much more quickly ready to predict that it's going to be heads because you know its behavior. So entropy is a way of measuring uncertainty, just like variance is a measure of uncertainty. The opposite of entropy is information, is what we actually call information in a principled way. If you do this calculation for Gaussians, which I think will be one of your homeworks, you will find that the entropy for a Gaussian is proportional to essentially the determinant of the covariance. It sort of makes sense. How much spread you have measures your uncertainty. To finish, I just want to make now a connection between maximal likelihood and information theory. The concept of entropy introduced by Shannon, half a century ago, so this is sort of one of the fundamental building blocks of our digital age, entropy information. This is what led to coding theory, and it's what makes us be able to chat with our friends on Facebook, what has enabled us to do that. Among other things. Now, to finish this, I'm going to connect entropy with maximal likelihood. And I apologize for going over this a little bit, but I will still take a break. The idea is, let's assume that there is a true theta. The universe has one true parameter. This is the true value of the distribution, the true mean of the Gaussian, or the true variance, the true neural network from which God is generating the universe as we see it, that true set of parameters. It's not far-fetched. If you think that we can simulate AI, maybe we're a simulated AI in another simulation, and so we basically are a sample of a model. I'll leave that for the philosophers. But let's assume, this is essentially what maximal likelihood is assuming, that there is a true process from nature that generates the data. And this data comes with some sort of distribution. Then maximal likelihood basically says, if these points are independent, take their product over every n observations and maximize that. Maximize each of the heights, each of the probabilities, the product of these heights. And if we do this in log space, I forgot to say this. We take logs because it's easier to do calculations by hand, but logs are also important in computers because if you multiply lots of small numbers, they go to zero very quickly. You get underflow problems. So always work in log space. It's a good, when playing with probabilities, get used to using logs. We can move this to logs. The monotonic transformation doesn't change the location of the optimal. Another thing, so basically the location of this max doesn't, if I sort of lift this a little bit, the location of the max doesn't change. Likewise, the location of the max doesn't change if I shift this curve up and down. So if I add a constant value to it, it's not changing the position of the max. And so that's what I'm going to do next. I'm going to add this constant value to it. And it's constant because the free variable here is theta. Theta naught is known, is the God parameter that's been given to us. And so I can add it without changing the maximum. And now I can combine the two because I have the log of a division. I can separate it into the subtraction of the logs. And now I'm going to do the reverse of Monte Carlo. Remember the Monte Carlo, the idea is we went from an expectation to a sum. Now I'm going to do the opposite. I'm going to assume that the number of points goes to infinity, and I'm going to use the law of large numbers such that as n goes to infinity, and actually I did one more thing here, which is I'm going to swap the order of this. So in other words, I'm multiplying by -1 so that my max becomes a min. And the reason why I'm doing this is so that because this thing here has a name. It's called the KL divergence. It's a key concept also from information theory. It measures, it's non-symmetric, so it's not a distance, but it basically measures the difference between the two distributions. If you have two probabilities and you want to know how far they are from each other, you would use this. It's always positive, and when the distributions are exactly the same, the KL will be 0. So KL is a good way, shall we say, of measuring the distance between the God distribution in our distribution. So our distribution is our line, which has parameters theta 1, theta 2. Theta is an unknown that we're trying to estimate. And theta naught is the true distribution. And so maximum likelihood, the idea of maximizing our searching for the model that maximizes the data can also be rephrased in information theory as minimizing this thing called the Kullback-Leibler divergence, which is also known as the relative entropy. Because we're taking a ratio. Okay. Now, I'm going to once again use the property of the log of a division. So log of A over B is log of A minus log of B. And I'm going to rewrite it in this form. Now, the negative of the integral of P log P is the entropy uncertainty. The positive value is what we call the information. So this quantity here on the left, this is the information of the distribution of God. So we say of the distribution of the true asymptotic value, the true mechanism that generated the data. This is the distribution, or this is the information in my model. And so basically what this is saying, maximum likelihood is essentially looking at the information in the data produced by nature, and it's comparing it or contrasting it, because there's a minus here, against the information of the data that my model produces. Because this is my model. Okay? So it's in both cases, assuming that the data came from the true observation model, I'm comparing the information in the model, the data that I imagine, against the data that I see. And maximum likelihood gives me the lens through which I compare things. I compare the hallucinations against the world through the concept of entropy, or information defined in this way. That's what it does. It's not the only way. And in fact, as we go, but it's important that you realize that behind all this math and maximizing probabilities, essentially what we're doing is we're comparing some statistic of what I imagine against some statistic of what I see. And when these things are different, that's when I will move my parameter theta, I will update it. And when the two are the same, there's nothing to minimize. I've reached the minimum, so I don't need to update my parameter theta. That's the basis of learning everything we're going to be looking at. Okay, so let's take a 5-minute break, and then I'm going to deal with this issue of vertical lines.